Hi, welcome to another episode of Everyday Metallurgy. Today we're going to learn more about hot work tool steel. I have a special guest, an old friend that I met many years ago. We have been separated for many years, but now we're back in business together. Uh, in this episode, Ingolf, he will tell about tool steels in general. What is it? Then he will dive into focus on hot work tool steel, and he will tell a little about the process method, the ingot casting, and the electroslag remelting technologies. And he will also dwell a little on different heat treatment to homogenize and some of these intermediate steps you never hear of when you talk about how to prepare a tool steel. Then he'll go into forging, and we will end this episode on cleanliness because we have made two episodes on this. Because episode 2 is about the application for hot work tool steel. It's about the properties. How do they work? What are they really good for? We're talking about typical defects in episode 2. And we talk about the future of tool steels. Where are we aiming? But we'll start with episode 1. Enjoy it with Ingolf and me. Hi, Ingolf.
Hi, Peter. I'm very happy to see you again.
Yeah, thank you, and welcome to a new episode on Everyday Metallurgy. Ingolf, we met many years ago when I was developing a new type of tool steels. And you were one of our esteemed customers, and I treated you very careful. And we have not met for more than 20 years, but we met this summer and we had a fantastic talk. And therefore, we agreed that we should make an episode together on hot work tool steel, because you might be among the European champions in hot work tool steels.
Thank you.
But Ingo, would you give a short introduction to who you are, and then we'll jump into the
All
topic.
right. Yes, will be pleasure. Yes, thank you, Peter. First of all, thanks for the invitation to be a guest in your videos. And then, of course, it has been probably 25 years that we had been intensively cooperating on some steel development. And well, then several things changed. I left the company, and so I might perhaps start with a short introduction. As you already mentioned, my name is Ingolf Schroff. I had studied materials science at the Clausthal University in Germany, a small university, and I got my diploma on materials science in 1985. From May 1985 to September 2003, I was with Thyssen Edelstahl, which then changed names to Thyssen Stahl and then later Edelstahl Witten Krefeld. And then in September 2003, I left that company and started to work with a German tool steel producer, Kind & Co. Kind & Co. was a family-owned, medium-sized steel company specialized on the production of hot work tool steels for applications like die casting, die forging, extrusion, and so on. And from the beginning, I was working in the field of quality aspects like complaints, like troubleshooting, but also very intensively on the consulting of customers. And that is what I did until the end of July when I retired. Well, and after starting retirement, I thought it would be good to continue a little bit working, and so I set up my small office called Werkstoffberatung Schroff, which means materials consulting Schroff. Yeah, and that has just started.
Yeah, and now we start the story over again. And what we're going to talk about is, what is tool steel? We typically separate in two fractions: the cold work tool steel, the hot work, and the high speed. Can you give a description on what defines these three groups?
Yeah, that is first of all, tool steel is certainly the one of the oldest steel groups anyway, because there were already some ancient historic or archaeologic findings showing that iron tools had been used to produce some goods for the households 2000 years ago and even longer. And I think then the first application was a kind of a forging in former centuries. And so we talk about a very old and historic group of steels.
Yeah.
And well, I think there is one standard, that international standard ISO 4957, which defines what a tool steel is. And it defines that these tool steels are made to handle and to work as a tool and to handle materials. According to this specification, the tool steels belong to the group of special steels. I might show it in a presentation if you like to keep our visitors aligned.
Yeah, feel free to share.
Check. So, Peter, as I said, we have the international standard ISO 4957, which says that tool steels are part of the group of special steels like engineering steels or stainless steels. Mm-hmm. And also the standard divides the group of tool steels into cold work tool steels, hot work tool steels, and high-speed tool steels. Then there is a dotted line. Below there is a group called plastic mold steels. This group does not belong to the tool steels according to the ISO, because the variety of steels needed for plastic molding is so wide, starting from cold work tool steels like D2 1.2379 over corrosion resistant steels or even hot work tool steels. And this could not be included in the standard. So this standard ISO 4957 defines numerous cold and hot work tool steels and high-speed steels. And it gives a definition what the difference between these groups is. The distinguishing feature between cold work, hot work, and high-speed tool steel is the surface temperature, which the tools have to withstand during operation without a modification of their properties. Mm-hmm. And then the standard says cold work tool steels are unalloyed or alloyed tool steels for applications with surface temperature usually below 200 degrees Celsius. Hot work tool steels are alloyed tool steels for applications with surface temperature usually above 200 degrees. The third group, the high-speed steels, are steel grades mainly used in cutting and shaping applications, which, due to their chemical composition, offer highest high temperature hardness and tempering resistance up to 600 degrees.
Yeah.
So this is certainly the definition of what is tool steel.
Yeah. So if we dig deeper into how these steel are manufactured, I remember when I was working with tool steel, many of the alloys, they were just melted and casted into a steel mold. Yeah. But some of them were remelted to remove the slag, the electro slag remelting process.
Yeah,
And that's typical. I think it was only for hot work steel they were remelted. It never for a cold work, as I remember it. What is the purpose of that? What is happening there?
The main purpose of remelting is to purify the steel and to give it a more homogeneous structure, solidification structure, especially for applications like die casting today. We need very large cross sections because nowadays even some underbodies of cars are cast in one piece, pieces which require die casting die with a weight of 60 tons per side.
Wow.
And you can imagine, of course, these are segmented dies, but you can imagine that it requires huge blocks and extreme homogeneity and toughness to withstand the loads in such an application.
Yeah.
And so we have generally 3 routes, and maybe I can show again. Yes, we have more or less 3 routes.
Yeah.
The so-called standard or open metallurgy, which in case of hot work tool steels is used for applications like die forging. Remelting metallurgy, which in most cases is electro slag remelting, but can also be vacuum arc remelting, and that is mainly used for hot work tool steels in applications like high pressure die casting, but we also find it in some applications like extrusion or some plastic molding applications where we need extreme high purity and very good homogeneity. And then there is the route of powder metallurgy, where the melt is atomized to fine powders, which are then compacted or sintered or are used in additive manufacturing. I'm sure you can explain that route much better than me.
Yeah.
I have concentrated on the first 2 routes here, which are, I would say, used mainly in the large cross sections that are needed for most hot work applications.
Yeah. Many tool steels, they are quite highly alloyed, and they form carbides. Some of them form carbides called primary carbides, so they solidify as a part of the solidification curve. Some of the carbides are secondary, so they do not appear until later as a segregation in solid state. When are they formed, and how are they controlled in these 2 processes?
They usually appear during or after the hot forming, during cooling from forming or rolling, and during the annealing processes which follow the shaping operations. Usually in hot work tool steels, we do not find the primary carbides. We find them more in the wear resistant cold work tool steels. But here in hot work tool steels, we mainly have so-called secondary or special carbides, which have the main elements as, of course, carbon and iron, but also then chromium, molybdenum, and vanadium, which provide, for example, the necessary secondary hardness maximum. They are responsible for very good high temperature strength and tempering resistance, and also, of course, for wear resistance.
Yep. And they cannot be controlled as a part of the solidification. So they, you can solidify and you can make the grains and they appear, but then you can heat treat it as a part of the post-processing where they disappear. You can fully remove them in a heat treatment. Is that right?
The secondary carbides, you mean?
Yes.
Yeah, but you are not supposed to solve them completely because they are also responsible for controlling the grain size. During the austenitization, when you harden a hot work tool, for example, you solve approximately 50% of the carbide which you have created during the earlier processes. And when you buy the hot work tool steel, it is usually in the so-called soft annealed condition. That means we have a ferritic matrix.
Mm-hmm.
And very numerous fine carbides, which usually have a fine spheric appearance and should be homogeneously dispersed in the matrix. So the carbon, which we then need later on for the hardening process, is more or less completely involved in the carbide formation at that moment. That means when we want to harden the tools, we need to solve a certain volume of the carbides so that the carbides then offer the necessary carbon for the martensitic transformation.
Because it's almost pure iron. The carbide has taken all the graphite.
Yes.
Yeah. If we look at the solidification pattern in the direct casted, how does that look? Is it big grains? I could imagine at the edge where you have the high cooling, you have very fine grains, and in the core of is it called coquille?
The mold or ingot.
Yeah, the mold.
The ingot mold, yes.
Yeah.
You have, of course, coarser grain size, coarser grains, and you have also precipitations on the grain boundaries because you give a lot of time in the center of a solidifying ingot. So that you will find precipitated carbides then on the grain boundaries. And that is certainly one of the reasons why hot work tool steel should not be used in the cast condition only. That means not only for shaping it is required to forge the material or to roll it, it is also required to break up the solidification structure.
Okay, so you are moving it around and creating new grains that are homogeneous inside.
Yes.
Size.
The more homogeneous, the better it is for the later applications, and especially if we imagine a large die casting die where you have deep excavations for the cavity for the shape of the part that you need to cast. Then you somehow machine within the center of the steel block. And then if you then encounter coarse grain, you have a comparably brittle behavior, and that is critical because coarse grain means brittle behavior and early fracture, early failure of the die.
What about the impurities? Are they only at the grain boundaries, or are they also inside the grains?
They are also inside the grains, as I understood this, yes. And of course, each impurity is like an internal notch. And that means for a good toughness behavior, we need to remove the inclusions, whether it is oxides or sulfides. We need to achieve a very high purity in the steel. And this is usually achieved by the Electro slag remelting process.
Yeah.
That is the most...
I would like to dig deeper into that. How does it work, and what is the slag level, the oxide level, or the sulfur level prior to the electroslag reforming, and what is it afterwards?
Okay, I try to go back to the PowerPoint.
Yeah.
Here is a survey of the two main production routes that we have. First, this standard metallurgy, which starts. Well, all processes usually start with scrap. That means worn-out tools are used as raw materials. So that is more or less a complete recycling process, which in these days is more and more important with regards to ecology and so on.
Yeah.
So we start with in the electric arc furnace or an induction furnace, depending on the company, where the melt is produced. The melt is then transferred into a ladle furnace where some alloying elements are added. It is vacuum degassed, and then they cast the melt into in the ingot casting process, or in some cases even in continuous casting, but that is very rare.
Yeah.
They cast round or rectangular or other shapes of ingots, which then are forged or rolled to different shapes. This forming process is then followed by a heat treatment process, which certainly includes several processes to transfer the material into the defined annealed, soft annealed condition. That means we have to follow some restrictions regarding the annealed hardness in which the material is sold. Then we also have in some applications restrictions regarding the so-called soft annealed microstructure. All that is done in the heat treatment processes. And then follows quality inspection before the material is sent to the warehouse or customer.
Yeah.
The remelting process starts again with the same process up to ingot casting. Then in the ingot casting process, we cast round ingots. That means not rectangular or any other shape, round ingots, which are then called electrode.
Yeah.
These electrodes are then transferred into the electric slag remelting equipment or into the vacuum arc remelting furnace. This is a time-consuming process which provides a very good homogeneity and cleanliness. Before then, the material is again forged or rolled and follows the same processes as above: heat treatment, quality inspection. That is more or less the way the material is produced. I did not make a sketch of the powder metallurgy route because that, in this case, I did not want to touch. First of all, it is only used for some, actually, as far as I understand, smaller hot work tools or tool inserts in highly stressed areas.
Yeah.
Besides that, I'm more familiar with the standard and with the remelting metallurgy.
Yeah. I would also, my personal view of making it powder route is if you are going powder, it's because you have elements in the steel that will segregate, that don't want to be a part of it. So you need an extremely rapid solidification to avoid clustering of primary carbide, it could be.
Yes, that is a very important aspect, that that you need to have this very fast solidification. And so far, it has not turned out to be necessary in these two traditional routes.
Yeah.
In the
I fully agree.
Yes, please.
Yeah. So if we look at that one, the ESR process, how does it really work? That is sometimes a bit difficult to understand what is happening inside that machine.
Yeah, perhaps we start with the conventional ingot casting. We have a cast iron mold that is filled usually from the bottom with the liquid steel, which then solidifies from the surface towards the core. We have a head section which is collecting impurities and will be cut off later. So this can be used for many standard applications like forging, for example, that material. But for applications with higher demands on toughness, mechanical properties, and so on, or if you have a very high alloy content, it is recommended to use a remelting technology. And in this case, the ESR or electro slag remelting technology. I mentioned that in this process we cast round ingots as the so-called electrode. That is here, this one. This electrode is immersed with the lower end into an artificial slag. That is a substance with a given composition. I cannot exactly say what the constituents of this slag are, but it works like a filter in the process. It is heated up to approximately 1,700 degrees. And so we need to know that the electrode as well as the bottom plate here are connected to electric power supply. And due to the electric resistance, the steel of the electrode starts to melt into droplets, which then pass the layer of the artificial and liquid slag. So under the slag, we have a melting pool in which we have a small volume of liquid purified steel. Then this whole process occurs in a mold, which is usually made of copper with installed water cooling. So we have a very fast or comparably fast solidification in the radial and also the axial direction. The solidification is much faster than in this traditional ingot casting if we compare similar cross sections. The next effect is that we have the purification and the comparably homogeneous solidification. But we also have the beneficial effect that we can create larger cross sections than before with the electrode. That means we can, for example, melt a round ESR ingot with a diameter of approximately 1,000 millimeter from an electrode with 750 millimeters diameter. So we can increase the achievable cross-section of the steel. That is necessary to fulfill the dimensional demands which we have nowadays.
And can you add more electrodes, make it almost continuous by, are they welded together or are they just stacked?
It depends on the equipment that you have. In some cases, you have a so-called sliding mold. That means the mold itself is stationary, but the newly solidified ingot, the ESR material, is moving down. And you can continue feeding from the top by inserting a new electrode. But in most cases, the melt shops try to avoid it, because whenever you have a change of electrode, you have a interruption of the melting process. So you get a small or short irregularity, because the new electrode is a little colder than the other one before. Yeah, it is difficult to add a new electrode, because the new electrode would be a little bit colder than the old worn-out electrode. And when you insert the new electrode into the liquid slag, you will cool it a little bit, and that will lead to some irregularities over the length of the ESR ingot. So one tries to avoid changing electrodes. In nowadays equipment, you can produce ESR ingots today with 17, maybe even 20 tons of weight, and the electrodes that you need correspond to the weight. So
it's single electrodes, 17 tons.
Yes, it is then usually one electrode. Yes.
Yeah. How thick is this layer of slag?
Oh, that has, I would guess, a thickness of around 10, 15 centimeters, if I am right. I'm not the melt specialist, but that is what I have seen. That's a layer of several centimeters at least.
Yeah. Is it used? Is it saturated and cannot be reused? So you have to get rid of it on the run?
You can recycle the used slag and add it into the process to a certain volume. So it is not to be wasted immediately. It can be reused in a certain volume.
Yeah. So after this, when you have a big ingot, then you said next step was the forging or rolling.
Yes.
Yeah. Can you take it directly? It's not hot any longer because it's water cooled. So this is cold. So you have to reheat it again.
It is still warm. You must imagine that during the process, we start with the process with a melting bath down here. And so the new ingot grows upwards.
Yeah.
And so at the end of the process, we are somewhere here where the solidification stops. But here the bottom is not yet cold. It is still, I would say, a few hundred degrees in temperature, whereas the top has just finished solidification. So the ingots then first have to be transferred into a furnace for homogenization, temperature homogenization, before they are then transferred into the furnace where they are heated up to forging temperature.
Okay.
And for several applications, or the ESR hot work tool steels get so-called diffusion annealing. That is temperature. That is a heat treatment and the temperature range of 1260 to 1280 degrees centigrade, where these solidified ingots are kept on that temperature for, depending on the cross section, 30 to 40 hours.
That is for what reason?
That is because the solidification is not completely homogeneous. We still have some macroscopic and, of course, microscopic inhomogeneities in the ESR ingot, but in order to further reduce the microscopic inhomogeneities, we do this diffusion annealing. So that with the help of the diffusion process, we can reduce the intensity of microscopic inhomogeneities.
So you keep it so long at such high temperature that even the chromium can walk around and homogenize and be fully perfectly distributed.
It will, of course, not be a completely homogeneous material because that nobody can afford with today's energy prices.
Yeah.
But from my point of view, it is not necessary to have it completely homogeneous, and it is probably not possible when you have a 20-ton ingot of hot work tool steel with, let's say, 1,000 millimeter diameter. You would spend days for such a process.
Yeah.
So you transfer it into a good condition of microscopic and macroscopic homogeneity before you start forging.
Yeah.
In most cases, the forming is done under forging presses. And for some purposes later, to smaller dimensions, it is then, depending on the company, also rolled to smaller dimensions.
Yeah.
Is there a rule of thumb or a real rule that says when you forge, you need to reduce the size with 50% or more to secure that you have it? You're breaking up the original solidification pattern,
Yeah,
and so is there a rule for how much you need to deform it? You said you started with 1 meter in diameter.
yeah. Of course, you cannot reach the final forging dimension in one heat. You need to reheat and go back to the forging press again for some further passages through the forging press. Yes, there is a more or less a rule of thumb regarding the cross-section of before and after forging, and that relation should be 3:1 minimum.
To ensure
Sometimes
that you break down the original grain structures and you have a right recrystallization.
that is correct, and also the achievable toughness improves a little bit like in a curve like this, that if the higher the rate of deformation is, the better shall be the later toughness potential.
Okay.
So the finer the grain structure is at the end, the better it is for the toughness. And toughness is certainly the most important property here in hot work applications.
Yeah. I forgot to ask about the cleanliness during the ESR. Typically, we talk about you have a certain level of ppm oxides or oxygen in the steel prior to and then after. What level can you go from and to?
Well, how shall I say? I don't know exactly the ppm levels. There is an old German method to measure the cleanliness. That means with the so-called K1 or K4 method. That means you take a microscopic sample, grind it and polish it, and then you check for the oxides and sulfides, and with some factors regarding the size and distribution of these inclusions, you come to a K1 value that is used for K1 value is used for applications like for remelted materials. Then the K1 value should be less than 10. For ESR material, the K4 value that starts from larger inclusions should be less than 20. So
it's a counting method.
It is a counting method, yes.
Yeah. So when we were young, we did it manually with the naked eye or under a microscope.
Yes.
But I guess today you ask a computer to do that counting.
There are computer methods now, and there is also a new way to measure the impurity levels according to ASTM. But in the tool steel in the tooling industry, this is not so widespread yet, because most people are more familiar with the traditional K1 and K4 values, at least here in Germany.
Yeah, that's fair.
Thank you for watching this first episode on the hot work tool steel. In next episode, we will dive deeper into the application for hot work tool steel. We'll dive into properties of hot work tool steel, polishability. We'll talk about corrosion resistance. We'll talk about typical defects. How do they break down, and how do you investigate that? Then we'll finally talk about the future of tool steels, and we will talk about where you can learn more. So sign up for this podcast, subscribe to it, and wait with patience for part 2. It will be there faster than you can recognize.